Russ Weeks here from PHEMI. He's a software architect, and he's going to talk to you about how PHEMI is leveraging Accumulo in the geospatial work they're working on. So, thank you.
Thanks, everybody. Right, so I'm here from PHEMI. We're a Vancouver, BC-based startup. We have a commercial product that we build called PHEMI Central. It's a data warehouse product on top of Accumulo. So I'm really grateful for the opportunity to speak here, and I'm very acutely aware that you guys didn't come here to hear a sales pitch about my product. So rather than tell you about how awesome PHEMI Central is and why you should all buy it, I'm going to try to focus on some of the cool things that we've been able to do because we're built on top of this amazing foundation of Apache Accumulo. So preventing bugs, putting Accumulo to work in the field. I was trying to fit another pun in there, but the organizers told me I was being a pest. But the use case, don't worry, I got plenty more of those. The use case we're going to talk about is precision agriculture. Precision agriculture is an emerging discipline in agronomy, and I'm going to start by saying I'm not an agronomist. And in fact, this talk is not totally about geospatial stuff, but I'm happy to be on that track, and I'm happy to follow the GeoWave guys. That was an amazing presentation. So precision agriculture, it's a discipline in agronomy that focuses on collecting and analyzing data to improve crop yields and reduce the likelihood and the extent of crop damage. And it's been really enabled by the proliferation of cheap, low-power, feature-rich wireless devices. So the lessons in precision agriculture are sort of more broadly applicable to other Internet of Things applications. This is what a typical deployment of a precision agriculture solution looks like. A farmer's going to hang a bunch of sort of solar-powered sensors from some of his trees, maybe one sensor every acre. The sensors are collecting environmental data, like temperature, wind speed, wind direction, humidity, device information like battery charge level, solar cell function, that kind of thing. And then every few minutes they forward this data to gateway devices, which are also sort of spread out across the field, about one gateway every 100 sensors. And the gateways typically have a beefier hardware profile, better CPU, bigger RAM, and crucially a wireless modem to get them onto a mobile data network. So the sensor data flows up through this tree topology, I'm so sorry, across a secure internet connection into Accumulo. And so I want to talk about what we do with it when it gets there. Sort of, Accumulo has three areas that really shine for precision agriculture. The first one are continuous aggregations, which the GeoWave guys just spoke about, and Coverse talked about yesterday. So, way to go, guys! Those are good talks. Continuous aggregations, taking advantage of Accumulo's server-side processing features, specifically the combiners, to produce incremental statistical values. Time series data, we'll talk about how we take advantage of Accumulo's distributed index to support low latency queries for time intervals. And spatiotemporal data, so this is getting into the geospatial stuff. We'll talk about the distributed data structures that we built on top of Accumulo to extend the one-dimensional index into higher dimensionality data. But before we get into that, I want to talk a little bit more about the value of precision agriculture and what it's good for. Precision agriculture is important because farming is risky. It's risky business. High-value crops like apples, oranges, pears, peaches require careful monitoring. Again, not an agronomist, but when I started looking at the number of things that can go wrong in an orchard, it's pretty terrifying. You have codling moths, which love to lay their eggs in apples. This is the nicest picture of a spoiled apple that I could find on the internet. It just gets worse from there, but it's just before lunch. So codling moths love to lay their eggs in apples, and farmers can't really get away with spraying their orchards every time they're worried about a pest infestation anymore, for a bunch of reasons. But the current state of the art is not to kill the codling moths, but instead to disrupt their mating cycles. And in order to do that, the farmers need very clear information about when the moths are going to start having babies. Frost damage. Frost can develop overnight, literally overnight, and it can destroy an entire crop's worth of fruit. Fire blight infestation. This is a really bad one. Fire blight bacteria can develop over a matter of a few days in an orchard, and if it's left unchecked. And what happens is the first year, you get a bad crop yield. The second year, you get no fruit at all. And then the third year, you tear up all your trees and start over again. So your entire orchard is destroyed. So as a farmer, being able to understand the way that the organisms are growing within your orchard is critical. And to vastly oversimplify everything, it comes down to the sun. When it's hot out, organisms grow quickly, and when it's cold out, organisms grow slowly. And this rate of growth is referred to as a degree hour or degree day, depending on the type of organism. I'm using the term organism very broadly here because this model is applicable to the bacteria, to the moths, and even to the fruit that's hanging from the trees. So rate of an organism's growth, degree hour, which means that the organism's rate of growth is a function of the temperature, which means that an organism's state of growth is expressed as the integral of that function. It can be expressed as the integral of that function over time. And this value is usually referred to as a cumulative degree day or a cumulative degree hour. And historically, it's been collected by a guy that goes out with his clipboard at noon and takes the temperature. It's 20 degrees, 70 degrees, sorry. It was colder in the morning, it's going to be colder in the evening, the temperature is going to follow this sinusoidal pattern, and I know how to calculate the area under the sine curve. But we can do better than that because we're getting this high-resolution data coming up from all these sensors in the field, hundreds of sensors across a farmer's orchard. So we get a very clear picture of the environment across the orchard. And if we run these temperatures through our growth models, we get a very accurate idea of their rates of growth over a given time period. And this is where Accumulo comes in, because if we sum up those values, we get a really good linear approximation of the area under that growth plot. And the combiner framework is an outstanding way to come up with that linear approximation. So this is kind of what our aggregation schema looks like for this use case. A sensor message comes in, we record the message. I'll get to how we record in just a sec. And then we pull out individual values and drop them into various time-based aggregation buckets. Some of the aggregations come directly from the message properties like temperature, wind speed, wind direction, humidity, that kind of thing. And other ones are calculated. For instance, degree hour calculations for codling moth, fire blight, dew point, wet bulb. More broadly speaking, what Gedalia said yesterday about commutative monoids in Accumulo really resonated with me because it's absolutely right that once you start looking at what kinds of problems can we solve with commutative monoids, you kind of can't stop thinking about it, right? There's top K, there's sampling, there's set cardinality, just it goes on, and diverging from agriculture here, the combiner framework is an outstanding execution environment for figuring that stuff out. It's really, I feel like it's one of the key strengths of Accumulo. So these are the aggregations that we build, and then obviously we take advantage of the fact that it's all indexed to produce very low latency access, so the farmers can see these aggregated values on the order of tens or hundreds of milliseconds. So the second area that I want to talk about is time series data. I think time series, it's probably a more conventional application for Accumulo. And in our scenario, precision agriculture, it comes down to those messages that the sensors are producing. So every sensor is producing a message every few minutes. They're getting aggregated up to Accumulo. And by the time they get there, it's a constant high velocity stream. And sometimes, a simple case is a user will want to say, they'll want to get an idea of the environment at a very localized query at a specific point in the orchard. Tell me about the environment of this spot over the last 2 weeks, or for network management purposes, just like what was happening to this sensor before it dropped off the grid. So it's a pretty conventional problem, and we started trying to solve it in a pretty conventional way. Message comes in, message gets a row ID. We parse the message, we extract some fields, we organize the fields into column families, sort of based internally on what we want to do. We build a message ID there by concatenating the sensor ID and the timestamp of the message. And then, the desired query is show me the last 2 weeks of data for a particular sensor. So, we lexicode and transpose. We build the transpose index, and now you want to find the last 2 weeks of data for a certain sensor. You take the sensor ID, You define your time range, works out to one interval. Across the row IDs, you do your scan, you get all the message IDs that you want. And then if you want to find the actual message data, all you have to do is go and dereference those row IDs in the raw data table, right? I think this is kind of how people build indexes on Accumulo. We thought we were done. I think this is probably a pretty common comment when you're presenting big data solutions to people that come from like a relational database world or a data warehousing world. And I'm being a little facetious because our users are interacting with our system through our REST interface, and our REST interface is interacting with Accumulo through the proxy. So the cost of dereferencing those message IDs, the RPCs, added up pretty quickly. And again, we're targeting, I want to be able to see the last 2 weeks of sensor data in a matter of milliseconds. So what we did was we took the frequently used properties, the most valuable properties out of the sensor message, and we embedded them in the index keys. So you can see here, we got battery, wind speed, temperature, whatever properties are going to be most frequently accessed get embedded into the index values. In addition to that, we have we still maintain the reference back to the original digital asset that generated the index values. So if you want to get the full set of values, you just have to dereference the ID. I think this is probably a pretty common pattern as well. This idea that I can trade off storage space for response time. We're pretty eager to do that in PHEMI Central generally, because I think we're we're coming at it from a different direction than many of the people in this room might be. We're dealing with people that are just getting to the point where a relational database is not an option for them anymore. Like an enterprise data warehouse is not an option. Maybe their license fees are killing them. Small, medium enterprises. So it's not like they have petabytes of data and a relational database has never been an option. It's like they're just getting to the point where they're exceeding their capacity. Maybe they have data that they don't want to throw away anymore, and they're looking at big data solutions. So we're pretty eager to trade off storage space for query performance. So the last area that I want to talk about is some of the stuff that we've done in the geospatial and spatiotemporal world. I'm going to be frank, our solution is not nearly as feature-rich as the one that you just saw if you were here for the GeoWave talk, which was pretty amazing. For precision agriculture, our solution is really focused on being able to identify potential frost risk. So frost, as I said, is pretty serious. It can destroy a crop overnight, all of the fruit in your crop, and it can develop quickly, sort of in a matter of minutes, and it's very expensive to mitigate. The way that you mitigate frost risk is you hitch a burner up to your tractor and you drive up and down your orchard and you literally warm up the outdoors. So it's costly. And the way you identify frost risk is you start by looking for signs of temperature inversion, cases where the temperature below the leaves of the tree is lower than the temperature above the leaves of the tree. And because it can develop so quickly, conventional ETL methods, like from an enterprise data warehousing architecture, are not really suitable here. You don't have the opportunity to do like a batch extract from an OLTP system into an OLAP system and build a data mart and do a query. The farmers really need low latency access to the absolutely most recent data that's available. So the spatiotemporal index in our product is also based on a Hilbert curve. It's a third order, two-dimensional curve. I'm assuming that a lot of people are hanging over from the GeoWave talk. So fourth order curve, sixth order curve, and again, the fractal property is, the decomposition of the curve in the smaller quadrants is very similar to the overall flow of the curve. This being a sixth order curve, there's 4,096 positions, which means that every latitude and longitude in that space gets put into one of those positions. I think we go up to a 23rd order curve for two-dimensional space and a 21st order curve for three-dimensional space, which gives us a I think something like a resolution of 150 meters by 150 meters by 15 minutes at the equator. We do the same thing as the GeoWave guys were talking about, in the sense that time is an unbounded dimension, so we bin it by years. So if you do a query that spans 2 or 3 years, then you're actually going to do 2 or 3 queries. But again, the common use case for agriculture is, for frost risk particularly, is I'm looking at the last 20 minutes of data. Right, so we extend it to the 3D use case. Show me the average temperature over this area, for this area over the last hour, 2 hours, 12 hours, that sort of thing. Like finding the areas that are prone to inversion or frost damage. And so this is what the three-dimensional curve looks like. And again, what it amounts to is that search area, which here is represented by the blue cuboid, almost never maps exactly to a nice set of intervals on a curve. Like for Accumulo, you'd like it that if a search area was like, works out to exactly one scan range, but that never happens. So you need a heuristic that can balance a search area which might get decomposed into like 50 or 100 disjoint curve intervals against, I guess what I'm saying is you could, if you merge some of those intervals together, you might get a little bit of slop in your query. You might get some values that are not actually, that are actually outside of your search cuboid, but you might be willing to accept that if it makes the query faster, if it reduces the number of scans that you have to do. So we have a heuristic that balances that, and then I think the standard approach is that you put a filter, an iterator on the server side to get rid of that slop. So you decompose your search volume into a bunch of intervals using your heuristic to optimize that. You do your scan against Accumulo with an iterator on it that's also been configured with your search volume to get rid of stuff that got left over. Honestly, this is not a question that any of our customers ask us. Again, because we're coming from the enterprise space, we're dealing with people that don't know Hadoop, that don't know Accumulo, that don't know HBase. So I'm going to get into the technical reasons of why not HBase, but just from a business perspective, when we talk, I've been following my sales guy around a lot. And when we talk to customers, they're impressed by the pedigree of Accumulo. They believe that having a product that came out of this community it gives it a credibility that it otherwise might not have around the security and the access control to the data. And then we can wow them with 100 million ingests per second, which is awesome. But the technical reasons, iterators are awesome. They're an amazing programming framework once you get used to how they work and what they can do. And the farmers that we talk to are interested in cell level security in the sense that they have different people at their farms that they'll bring in consultants that might be able to analyze temperature data but not necessarily see crop yields. They can work with their neighbors who might also be their competitors to share some of the, excuse me just a sec. Whoa. Going back. They can work with their competitors, who might be their neighbors, to share environmental data, but they don't want their neighbors to see their how many pests are in their fields, that kind of thing. And then there's also a really interesting movement underway to share that agricultural data with industrial partners that are helping them, selling them stuff for their farm. So that's about it. I think we got lots of time for questions. So the heuristic behind the actual decomposition is just that the space, we have just a uniform decomposition, right? Like you start off at the top level at a very low resolution, and then as you go down, the for a 3D curve, it gets broken down into octants, and each octant is of equal volume. The GeoWave guys showed something very interesting around how you can scale the different dimensions to say I'm interested in higher resolution for time and perhaps less high resolution for space. It's a pretty powerful feature that I think we're going to look closely at, but for this use case, it's the uniform decomposition is okay. So that's a good question. The question was, do our customers run a copy of this locally on their farm? And generally, no. So for precision agriculture, they are typically happy for us to host it either on our premises or in AWS. Our core competency is sort of in healthcare, healthcare organizations in Canada, and that's a very different space. They're uniformly interested in on-premises solutions and disinterested, antagonistic towards cloud-based solutions. Good question. Yeah, so the question was, why didn't we just use GeoWave or GeoMesa for the spatiotemporal stuff? And the answer is kind of multifaceted. The spatiotemporal features are a significant but small part of PHEMI Central, which again, I'm not trying to pitch, but we have a feature set around curating relational data sets and data governance and data sharing and stuff. So I guess what I'm getting at is it wasn't core to it's not core to our product, and it wasn't clear to us how much work it was going to be to integrate GeoWave or GeoMesa versus to build a solution that met our immediate customers' needs. Okay. Well, I guess that's it. Thank you very much.